Greetings. I am Dr. Abraham P. Detrench Kallon, and today we will explore the intricate subject of quantum computing. This lecture aims to provide a comprehensive understanding of quantum computing, tracing its origins, examining its evolution, and discussing its future potential and benefits for our society and beyond. Lecture on quantum computing, from its inception, the evolution, and its future of opportunities. Introduction to quantum computing. Quantum computing is a revolutionary field of study that leverages the principles of quantum mechanics to process information in fundamentally new ways. Unlike classical computing, which relies on bits, zeros, and ones, quantum computing operates on quantum bits or qubits, enabling parallel processing, superposition, and entanglement. The development of quantum computing has been fueled by advancements in quantum physics, mathematics, and engineering. Scientists and researchers aim to harness its power to solve complex problems that are beyond the reach of classical computers. 1. Historical background and evolution of quantum computing. Early foundations. The birth of quantum mechanics. The principles that led to quantum computing originated from quantum mechanics, a branch of physics developed in the early 20th century. Some key milestones include 1900, Max Planck introduced quantum theory, explaining blackbody radiation. 1925 to 1927. Werner Heisenberg and Erwin Schrödinger formulated quantum mechanics. 1935. Albert Einstein, Boris Podolsky, and Nathan Rosen introduced the EPI paradox, discussing quantum entanglement. The concept of quantum information processing. The idea of quantum computing emerged when physicists explored the application of quantum mechanics to computation. 1981. Richard Feynman proposed using quantum mechanics for computation, noting that classical computers struggled to simulate quantum systems. 1985, David Deutsch formulated the concept of a quantum Turing machine, laying the groundwork for quantum algorithms. 1994, Peter Shor developed Shor's algorithm, showing how quantum computers could factor large numbers exponentially faster than classical computers. Early experiments and first quantum computers. 1996, Love Grover introduced Grover's algorithm, which speeds up database searches. 2001, IBM demonstrated Shor's algorithm on a small-scale quantum system. 2011, D-Wave announced the first commercial quantum computer, albeit controversial in its claims of quantum advantage. 2. Core principles of quantum computing qubits. The fundamental unit of quantum computing. A qubit is the quantum version of a classical bit, but with unique properties. Superposition. A qubit can exist in multiple states, zeros and ones, simultaneously. Entanglement. Qubits can be correlated in ways that classical bits cannot, allowing for faster information processing. Quantum interference. The ability to manipulate quantum states to improve computational results. Quantum gates and circuits. Quantum computing uses quantum gates, which are different from classical logic gates. Hadamard gates, H, creates superposition. Polygates, X, Y, Z, perform quantum state transformations. CNR gate, a 2-qubit gate that generates entanglement. Toffoli gate, a quantum version of an AND gate. Quantum circuits are formed by applying these gates in sequences to perform computations. 3. Quantum computing models and implementations. Gate-based quantum computing models and implementations. Gate-based quantum computing. This is the most common model, where quantum gates manipulate qubits similarly to classical logic circuits. Quantum annealing. Used by companies like D-Wave, quantum annealing focuses on solving optimization problems by finding the lowest energy state of a system. Topological quantum computing. A theoretical model that uses anyons, exotic particles, to perform error-resistant quantum computations. 4. Quantum algorithms and applications. Shor's algorithm, factoring. Efficiently factors large numbers, threatening classical cryptography systems, RSA encryption. Grover's algorithm, search, speeds up searching in unstructured databases by n times faster than classical search algorithms. Quantum machine learning enhances AI and machine learning tasks by improving optimization, pattern recognition, and complex data analysis. Quantum cryptography, quantum key distribution, QKD, enables unbreakable encryption using the principles of quantum mechanics, drug discovery, and material science. Quantum computing can model complex molecules and chemical reactions, significantly advancing pharmaceuticals and materials engineering. Financial modeling and optimization. Banks and financial institutions use quantum computing to optimize investment strategies and risk assessments. 5. Development of quantum computing. Current status: leading companies in quantum computing. Several companies are leading the charge in quantum computing research and development. IBM developed the IBM Quantum Experience and superconducting qubits. Google achieved quantum supremacy in 2019 with a 53-qubit processor. Microsoft works on topological qubits with its Azure Quantum Initiative. D-Wave specializes in quantum annealing computers. Intel, researching silicon-based quantum computing. Challenges in quantum computing. Despite advancements, quantum computing faces significant hurdles. Quantum decoherence. Qubits lose their quantum state due to environmental interactions. Error correction. Quantum error correction is necessary but highly resource-intensive. Scalability. Scaling quantum systems to thousands of qubits remains a challenge. 6. Future of quantum computing near-term developments. Quantum cloud computing. IBM, Microsoft, and Google offer quantum computing services via the cloud. Hybrid computing, combining quantum and classical computing to maximize efficiency. Long-term vision. Cryptographic revolution. Quantum computing threatens current encryption, leading to the rise of post-quantum cryptography. Artificial general intelligence, AGI. Quantum computing could accelerate AI research toward AGI interdisciplinary research. Quantum computing will impact fields like biology, physics, and economics. Potential job opportunities in quantum computing. Quantum software engineer, quantum algorithm developer, quantum physicist, quantum hardware engineer, quantum cryptography expert, quantum AI researcher. Quantum computing represents one of the most exciting frontiers in modern technology. From its theoretical foundation in quantum mechanics to today's cutting-edge research and corporate investments, it has the potential to revolutionize fields such as cryptography, artificial intelligence, material science, and optimization problems. While significant challenges remain, rapid advancements indicate a future where quantum computing could become a transformative force across industries. The journey from classical to quantum computing is still unfolding, and those who invest in learning about this field today will be at the forefront of the next technological revolution. Recent developments in quantum computing by major tech companies. In recent months, leading technology companies such as Amazon, Microsoft, and Google have made significant strides in quantum computing, each unveiling new quantum chips designed to enhance the performance and reliability of quantum systems. Amazon's Ocelot quantum chip. Amazon's Ocelot quantum chip. Amazon Web Services, AWS, introduced its first quantum computing chip, named Ocelot, marking a pivotal step in the company's quantum computing research. The Ocelot chip employs cat qubits, which are engineered to suppress specific types of errors, thereby reducing the need for extensive error correction. This innovation aims to make quantum error correction up to 90% more efficient compared to existing methods. Currently, Ocelot is a research prototype and not yet commercially available. Microsoft's Majorana 1 quantum chip. Shortly before Amazon's announcement, Microsoft unveiled its own quantum computing chip, dubbed Majorana 1. This chip represents a significant advancement in Microsoft's approach to building scalable and stable quantum computers. While specific details about the chip's architecture have not been extensively disclosed, it underscores Microsoft's commitment to overcoming the challenges inherent in quantum computing, particularly those related to qubit stability and error rates. Google's Willow quantum chip. In December 2024, Google announced a breakthrough in quantum computing with its Willow quantum chip. This chip addresses the long-standing issue of qubit errors that increase with scale. Google's innovation involves creating a more stable virtual logical qubit by using multiple qubits to correct errors, leading to more stable outcomes as the number of qubits increases. This development is a significant step toward building functional quantum computers capable of solving complex problems beyond the reach of classical computers. Understanding bits and qubits. To comprehend the advancements in quantum computing, it's essential to understand the fundamental difference between classical bits and quantum bits, or qubits. Bits. In classical computing, a bit is the basic unit of information, which can exist in one of two states, 0 or 1. Computations are performed by manipulating these bits through logical operations, qubits. In quantum computing, a qubit serves as the fundamental unit of information. Unlike classical bits, qubits can exist in a state of 0, 1, or any quantum superposition of these states. This means a qubit can represent both 0 and 1 simultaneously, a property known as superposition. Additionally, qubits can exhibit entanglement, where the state of one qubit is directly related to the state of another, regardless of distance. Qubit volume compared to bits. The concept of volume in terms of information capacity differs between bits and qubits due to the principles of superposition and entanglement. While a classical bit can represent a single binary value at any moment, a qubit can represent multiple values simultaneously. Specifically, a system with n qubits can represent 2 circumflex n possible states at once, whereas in classical bits can represent only one of 2 circumflex n possible states at a time. This exponential growth in representational capacity is what gives quantum computers their potential advantage over classical systems. Effectiveness of qubits in quantum computing. Quantum computing's potential superiority over classical computing stems from the unique properties of qubits. Parallelism. Due to superposition, quantum computers can process a vast number of possibilities simultaneously, enabling them to tackle complex problems more efficiently than classical computers. Entanglement. This property allows qubits to be interconnected such that the state of one qubit can instantaneously influence the state of another. Entanglement is crucial for certain quantum algorithms that outperform their classical counterparts. These properties enable quantum computers to address specific computational challenges more effectively than classical computers, particularly in areas like cryptography, optimization, and simulation of quantum systems. However, practical implementation faces challenges, notably qubit stability and error correction. The recent developments by Amazon, Microsoft, and Google aim to mitigate these issues, bringing the realization of practical quantum computing closer to fruition. For a more in-depth understanding of the differences between bits and qubits, you might find the following video informative. As a professional looking to deepen your expertise in quantum computing, there are several additional aspects that are critical to understanding its full potential, limitations, and real-world applications. Here are key areas that I haven't covered in detail but are crucial for a well-rounded knowledge of quantum computing. 1. Quantum error correction, QEC, and fault tolerance. One of the biggest challenges in quantum computing is dealing with quantum decoherence and errors caused by environmental noise. Classical computers have robust error correction, but quantum computers require quantum error correction, QEC, techniques due to the fragile nature of qubits. Logical qubits versus physical qubits. A logical qubit is a stable, error-corrected version of multiple physical qubits. Surface code QEC, one of the most promising error correction techniques that encodes logical qubits in an array of physical qubits. Threshold theorem. If the error rate per qubit operation is below a certain threshold, quantum error correction can make computations arbitrarily accurate. Without effective QEC, large-scale quantum computing is impossible. Companies like Google and IBM are focusing on reducing physical qubits error rates and developing better fault-tolerant architectures. 2. Quantum hardware architectures. Different quantum computing models use different physical systems to implement qubits, used by Google, IBM, and Rigetti. Qubits are created using Josephson junctions cooled to near absolute zero, trapped ion queues used by IonQ, Honeywell, and University of Innsbruck. Qubits are stored in individual ions trapped by electromagnetic fields. Photonic quantum computing, used by Xanadu and C-Quantum. Qubits are represented by light particles, offering potential for high-speed communication and networking. Topological qubits, pursued by Microsoft. Theoretically more stable, but still under development. Neutral atom computing, a growing alternative using laser-manipulated neutral atoms as qubits. Each hardware approach has its advantages and disadvantages in terms of coherence time, error rates, scalability, and connectivity. 3. Quantum cloud computing and accessibility. Quantum computing is still in its early stages, and full-fledged quantum hardware is not yet widely available. However, quantum as a service, QaaS, platforms provide cloud-based access to quantum computing. IBM Quantum Experience. Free and commercial access to IBM's quantum processors. Google Quantum AI, CIRC. Open source tools and cloud-based access to quantum computing. Microsoft Azure Quantum provides a range of quantum computing backends, including IonQ, Honeywell, and QCI. Amazon Braket, AWS's platform, allowing users to experiment with different quantum hardware vendors. These platforms allow researchers and professionals to experiment with quantum algorithms before large-scale quantum computers become practical. 4. Quantum machine learning, QML, and AI in quantum computing. The intersection of quantum computing and artificial intelligence, AI, is one of the most exciting areas of research. Quantum computers can potentially accelerate AI training, optimize machine learning models, and improve pattern recognition. Quantum support vector machines, QSVM, uses quantum kernel estimation for better classification in AI models. Quantum neural networks, QNN, theoretical models of AI that could leverage quantum parallelism. Quantum Boltzmann machines, QBM, used in deep learning to model probability distributions more efficiently. Hybrid quantum classical AI, a model where quantum algorithms enhance certain parts of classical AI pipelines. Companies like Google, IBM, and Xanadu are actively researching quantum AI applications. 5. Post-quantum cryptography, PQC, and security implications. Once large-scale quantum computers become available, they will break modern encryption protocols based on RSA, ECC, and Diffie-Hellman, which rely on the difficulty of factoring large numbers. Quantum-safe cryptography, PQC. Researchers are developing encryption methods that remain secure even against quantum computers. Lattice-based cryptography, a promising alternative resistant to quantum attacks. Quantum key distribution, QKD, uses quantum mechanics to create unbreakable encryption, already being tested for secure communications. Organizations should start planning quantum-resistant security strategies as quantum computers evolve. 6. Quantum Internet and quantum networking. Beyond computing, quantum mechanics is enabling quantum communication and the idea of a quantum internet, which could allow unhackable data transmission and global quantum computing networks. Quantum teleportation uses entanglement to transfer quantum states over long distances. Quantum repeaters, essential for building long-range quantum communication networks. China's Misha satellite demonstrated long-distance quantum secure communication. Quantum networking could revolutionize cybersecurity, cloud computing, and global information exchange. 7. Quantum computing in industry applications. Beyond theory, quantum computing is making an impact across industries. Healthcare and pharmaceuticals, simulating molecular interactions to speed up drug discovery. For example, Roche and Boehringer Ingelheim. Finance, optimizing risk assessment and fraud detection. For example, Goldman Sachs and JP Morgan Chase. Logistics and supply chain, solving complex routing and optimization problems. For example, Volkswagen, Airbus. Energy and materials science, developing new materials and optimizing energy usage. For example, ExxonMobil, BASF. Understanding industry applications can help professionals position themselves in quantum computing career paths. 8. Careers and skills in quantum computing. Quantum computing is an interdisciplinary field requiring expertise in quantum physics, understanding qubits, superposition, entanglement, and decoherence, mathematics, linear algebra, probability, and complex numbers are critical. Computer science and software development. Quantum programming languages such as Qiskit, IBM, Python-based quantum programming framework, CIRC, Google, for designing and simulating quantum circuits, Quipper, functional quantum programming language, Silk, new high-level quantum programming language, machine learning and AI, quantum AI and quantum-enhanced learning models. Professionals should upskill in quantum programming, algorithms, and error correction to stay competitive. 9. The future of quantum supremacy and practical quantum advantage. Quantum supremacy, achieved by Google in 2019. When a quantum computer performs a task that no classical computer can do in a reasonable time. Quantum advantage, the point where quantum computers provide practical benefits for real-world applications. We are still far from full practical quantum advantage. but advancements in hardware, software, and error correction are steadily bringing us closer. For professionals in the quantum computing space, keeping up with research, industry trends, and hands-on experience is key to staying relevant. Next steps for professionals. 1. Learn quantum programming. Start with Qiskit Circ or Azure Quantum. 2. Experiment on cloud-based quantum computers. Use IBM Quantum Experience, Amazon Braket, or Microsoft Azure Quantum. 3. Follow research papers and conferences. Keep up with Nature Quantum, ArcSieve, and IDE Quantum, ArcSieve, and IEE Quantum. 4. Join quantum communities and networks. Engage with Quantum Open Source Foundation, QOSF, Qiskit Community, or Quantum Computing Stack Exchange. 5. Develop use cases for your industry, whether in finance, healthcare, logistics, or security. Quantum computing will disrupt multiple industries. Quantum computing is an exponentially growing field, and professionals who position themselves at the forefront today will shape the future of computing, security, AI, and beyond. I appreciate your engagement in this discourse and encourage you to disseminate this knowledge to educate, inform, inspire, and motivate others. My name is Dr. Abraham P. Detrench Kallon. Thank you for your attention, and I wish you a productive day ahead.